When long-distance transmission cables are used, designers typically look for transmitters with higher drive strength. This can be difficult to locate, though, as many RS-485 transceivers will only state the drive strength to be 1.5 volts across a 54-ohm load. This is because manufacturers design their transmitters to be within RS-485 specification and may not have spec'd their transmitters for higher drive strength. There are manufacturers of transmitters in the market, however, which do specify higher drive strength capability. Higher drive strength transmitters are able to support a further communication distance at low data rates because the high drive strength allows for the transmitter to overcome parasitic DC resistance of the transmission cable. When higher data rates across long transmission cables are used, the transmitter's output signal will end up being attenuated at the receiver end due to the parasitic RC filter created by the cabling. This means for higher data rates, the communication distance limit is more affected by the cable quality and less by the transmitter's drive strength. In short, if further communication distance is required at high data rates, the transmission cable should be evaluated first, since it has a larger effect against the communication distance. A common question when discussing RS-485 is the maximum cable distance which transceivers can communicate across. The answer to this question depends on numerous factors which include but are not limited to data rate, allowable jitter, cable quality, mismatches in characteristic cable impedance, and termination resistance tolerance. This slide provides a conservative look at communication length in relation to data rate. Notice that there are 3 points labeled beneath the dark black line. In Region 1, the maximum distance is determined by the DC resistance of the cable. Here, the DC resistance of the cable approaches the value of the termination resistor, reduces the DC differential voltage appearing at the receiver by half. For a 22 AWG cable with a 120 ohm characteristic impedance and unshielded twisted pair, this occurs at approximately 1,200 meters. Region 2 shows the inverse relationship between bus length and data rate. Because transmission line losses increase with cable length, the data rate must be decreased in order to maintain an equivalent level of jitter. The transmission line loss here is contributed by a low-pass filter generated by the parasitic capacitance and resistance in the cable. In Region 3 above, the maximum data rate for any distance is determined by the maximum rise or fall time of the driver. For reliable communication, the maximum rise time or fall time of the driver should be no more than 1/3 of the total bit time at a given data rate. Although RS-485 standard recommends a maximum of 10 megabits per second, transceivers today are capable of operating up to 50 megabits per second. This slide provides an example of an eye diagram of the output and input of the cable transmission end. The input pin D before the transceiver and the output pin R after the transceiver are included. The cable length here is 1.2 kilometers at a data rate of 100 kilobits per second. On the left-hand side, the output can be observed, which seems to show an almost instantaneous rising and falling edge, while the receiver sees rising and falling edges which look like RC constants due to the cable parasitics. The output denoted as R can be seen transitioning at almost the same time each bit flip, and the jitter present on the cable receiver looks to be minimum compared to the bit width. This slide provides the same look as the previous slide, but the data rate changes from 100 kilobits per second to 1 megabits per second. The jitter present on the cable receiver end is much wider in comparison to the bit width in the previous slide. The output R can be observed to trigger at much different times due to the additional noise which can be seen on the cable end's receiver. This will generate varying bit widths, which may cause errors depending on the data protocol being used. When evaluating a particular link, the most critical factor is generally the insertion loss of the transmission line. This needs to be known across the frequency range of the data being sent. But how much insertion loss is too much? This depends on how much jitter the receiving system can tolerate. A good rule of thumb is that the insertion loss should be less than about 6 to 8 decibels at the Nyquist frequency, which is equal to the data rate divided by 2. For example, 500 kilohertz for a 1 megabits per second signal. Additionally, system designers should choose receivers with positive and negative input thresholds, which are symmetrical and close to zero in order to minimize duty cycle distortion.